Hi everyone, my name's Krish, and today I'm going to be talking to you about factors that affect the rate of reaction in GCSE chemistry and onwards. So this is actually a relatively simple topic, but students, even at A level, find it quite challenging to get their heads around. So I'm going to be using a few different analogies to kind of make it make more sense. The way I recommend learning this, if you're doing it at home, is listening to what I say and then only noting down the stuff on the PowerPoint once I finish talking. This is a trick I learned from my own physics teacher in school, and it proved to be very effective because that meant we were listening to everything he was saying very carefully rather than being too busy taking notes. So let's start with the kind of reaction requirements. What do we actually need for a reaction to occur? First of all, what is a reaction? It's basically when you've taken something and essentially turned it into something else, right? So you basically have what we call reactants. Now, these are two different compounds or chemicals, and we put them together and we want a third object out of them, okay? So essentially that's the useful thing at the end that we get. Now, you can think of this like the two reactants are school kids in a playground, okay? So you've got a playground, you've got some year 7s and some year 8s, and you've put them together in like a sort of football game, and the objective is to see who wins the game, okay? Think of winning as the product and the school kids as the reactant. Now, these school kids, they're running around all the time, so every now and then they bump into each other, okay? That's just how it happens. But in order for them to be successfully playing the game, we don't just want them bumping into each other aimlessly. We want them to be, tackling each other and scoring goals. That's why we need these collisions that are happening all the time to be successful collisions, okay? It's no point me and you bumping into each other if nothing happens. We want there to be a certain amount of energy in the bumping, okay? That means that if I have the ball and you tackle me, okay, you're able to take the ball from me, and that is what we will call a successful collision. For that to occur, there needs to be a certain amount of energy that both particles contain. So the person being tackled and the person doing the tackling both need to collide with a certain amount of energy. And that's what we will call a successful collision. And in order for a reaction to occur, that's what we need. So there are a few factors that affect this rate of successful collisions, because essentially the rate of reaction is how many successful collisions can we get and how quickly we can get them. So these are the four factors, okay? Temperature, concentration, particle size, and catalysts. Now, we're going to be breaking down each of these a little bit more to see why we get the effect that we do. So let's start with temperature. What is temperature? Heat and cold, right? Hot and cold, those are basically how we see temperature, those two words. Now, when someone is hot, they start to, sweat. You feel more energetic usually, right? When you're cold, you're more sluggish. Whereas in summer, we will have more energy. That's because heat is thermal energy, okay? So when you heat up a bowl of water, for example, you're giving it thermal energy. Now let's go back to the playground analogy to make more sense of this. So imagine now you've gone back to the playground full of year 7s and year 8s, okay? And you've given them each a sugar rush, let's say, okay? Some chocolate maybe. Let's pretend that that chocolate is our heat source and it's given them thermal energy. Now that they've taken this energy inside of them, they're going to have a sudden sugar rush. And what they're going to start doing is running around a lot more, with a lot more energy, okay, because they have more energy. So what's happened here is that the heat, the thermal energy, has converted into kinetic energy. Kinetic energy is movement. Remember that, yeah? So thermal is heat, kinetic is movement. This kinetic energy means they're moving more. They're going to vibrate more. The crucial term here is more, because remember, particles are always moving. The kids in the playground are always running around. It's just about how quickly they run around. When you give them that energy, when you heat up that playground, they're going to run a lot faster. And if they're running faster, they're going to collide into each other more often, first of all, because they're covering larger distances more quickly, right? And they're also going to collide with each other with more energy. Think of it. If you're just walking and you bump into someone, it doesn't really hurt. But if you're sprinting head on at them and they're doing the same at you, It's going to hurt. It's going to be like a rugby game, right? That's why when you increase the temperature, you are increasing the thermal energy, which is converted into kinetic energy, which makes the particles or the students in the playground vibrate more. Therefore, they collide with each other more often, and each collision is a little bit harder because they're running, essentially, okay, rather than walking. This means you have more successful collisions, because if you're moving faster and you're colliding harder, there's more chance that you're successfully going to tackle the person you're taking the football from, okay? So therefore, the rate of reaction is now going to increase because you're having more successful collisions. So now let's talk about concentration. Concentration simply means how much of something there is. So if you increase the concentration of the reactants, remember the reactants are the things that collide with each other to make the product, which is what we want. So if we increase the number of reacting particles, it's just going to be more crowded, right? So think of the playground again. Imagine at first you only had 100 students. Now imagine you've upped it to 1,000. They're going to collide more often because there's less space for them to run around in, because the size of the playground hasn't changed, but the number of kids has. They're going to bump into each other more often, and as they do that, the likelihood that some of these bumps are going to be successful collisions, successful tackles, is going to increase, and the end result of that is an increased rate of reaction there as well. Now, particle size is a little bit harder to wrap our heads around, okay? So you would think that the larger the particles are, the more successful the collision is, just because we have a way of, thinking bigger is always better. But in this case, that's not the case. Imagine you've got a cake, okay, a massive cake. Now, this cake is going to be hard to eat, okay? Now, let's say there's 6 people that want to eat this cake. They can't all eat the cake themselves, right? You have to cut the cake up. Now, imagine this in a reaction scenario. So we've got our cake, okay? That's the reactant. We've got the reactant particle, which is the cake. And the people that want to eat the cake are the enzymes. We'll talk about what enzymes are in a second, but essentially enzymes increase the rate of reaction. Okay, that will be coming up next. But essentially what this means is if we take one big particle, it's hard for the enzymes to get at it, right? There's not that many angles they can use. Now, if you cut this particle up into smaller pieces, if we've sliced our cake, there's more surface area for enzymes to eat, right? Because now each enzyme can pick up its slice of cake and eat it from any direction that it wants. This means that the smaller the size of the particle, the higher the rate of reaction. The exact physics of this, because that is physics in this part of chemistry, is a bit more complicated, but you don't really need to worry about the kind of nitty-gritty until A level. Just use logic in your own head to visualize a big object being cut into smaller objects, and understand that because you've done that, you've cut that cake up into smaller pieces, enzymes can eat the cake from different directions, and that will increase the rate of reaction. Now, finally, we also need to think about catalysts. Now, what is a catalyst? It's that thing we just spoke about, the enzyme. It's an extra ingredient that you add to the reaction. It does not get used up. Okay, so at the end of the reaction, you've got the product and the catalyst, and you have to separate the two. So the catalyst is not used up. Now, enzymes are what we call biological catalysts. So things that occur naturally in the body, for example, in biology, that increase the rate of reaction without being used up. Now, these always increase the rate of reaction. Think of them as basically additional reactants that don't necessarily take part in the reaction itself. So they kind of observe and help. Okay, so they give advice, think of it like that, rather than actually jumping in and playing the game of football. They'll sit on the outside like the parents, telling the school kids where to run and how quickly to run, and helping them out a little bit, okay? So that's how the rate of reaction increases. Before catalysts like enzymes to work, you need optimum conditions. So for example, many of the enzymes in the human body function best at 37 degrees Celsius, which is why our natural body temperature is 37 degrees, so that we can have the reactions that we need to survive running at the optimal rate. Enzymes and catalysts are also specific. Okay, so the way they're shaped is that they can only catalyze one reaction Okay, so enzyme X will always only be able to to be able to take part in reaction Y. Okay, so X and Y will go together, and that will always be the case. One catalyst can only be used for one reactant. Okay, and that is the end of our little lecture here. Hopefully that helped.